So, you may have heard people say such things as AI is in a bubble, and it is certain to incinerate billions of dollars. This is something that many people have said. And you may have heard people say AI will never become commercially adopted, or artificial general intelligence is just not feasible. It's completely impossible. These are all things that one side of the community is saying. But on the other side, you hear people saying things such as, we will have artificial general intelligence by September 2024. You may know who claimed that one. You may hear AI is the end of civilization as we know it within a decade. Or you might hear people say scaling compute is all we need to achieve superintelligence within the next 5 years. So we have two opposite sides here. And the worst part of all is there is extremely smart people on both of these sides. The side where AI is not going anywhere, or the side where AI is either solving all world problems or is the cause of all world problems because of how transformative and powerful it is destined to be in a very short time frame. And my goal in this video is to provide you with the evidence, research, and science behind this technology so that you can form your own opinion. And then I'll share my hypothesis and my analysis from a mathematical, scientific, and philosophical point of view. So there's 6 topics we're going to be discussing specifically. And largely what we're going into is the viability of this technology in the future. So there's the theoretical limits of generative AI. That is topic 1. Topic 2 is the transformer architecture and the theoretical limits of that. Number 3 is neuroscience and how it relates to current AI models. And number 4 is the current paradigm of computation that we are in. So there's like classical computers, quantum computers. Now there's thermodynamic computers being invented. And then next is the energy and costs associated with getting to the point where this is going to be widely commercially adopted. And then lastly, and this is actually where we're going to start off, is the current trajectory of artificial intelligence and the vocalized plans by the leaders who are building these technologies, because largely they're the ones steering the boat. So it's very important to understand where they want to steer it. And then throughout this presentation, we will be reflecting on different research papers, tests, benchmarks, including the ARC AGI test, which is claimed to be the only true AGI test benchmarking evaluation for current artificial intelligence models. And here's just a few different screenshots from the actual ARC AGI test. On the bottom right, you can see some examples of tests. My head might actually be in the way for the very bottom right one. But you can see on the test example to the left of my head that there is the input and then the output. And basically in the output, you're basically just filling in the holes on the squares. So you're basically just filling in the bottom right, bottom left, top right, and top left squares to complete the actual test. Very simple, but large language models can't do that. And then you can see in the chart above my head the actual performance of the progress of the current large language models on this test compared to other tests. Obviously, we've passed the Turing test by now with artificial intelligence. It's hard to tell just by talking with this thing whether it's human or not, but what we can do is put it through logic and reasoning-based tests to decipher how powerful is this model actually at generalizing reasoning and just approaching problems from a different point of view. And then one thing I think it's very important to do before we jump into the video is define what is AGI anyways, because this is a very loose term and not many people have a good definition of it. So there is a consensus argument or a consensus definition, but it is, quote, wrong according to the ARC test. And the consensus is AGI is a system that can automate the majority of economically valuable work. This is the consensus for AGI, but is claimed to be wrong. The correct definition, according to the ARC AGI test, is AGI is a system that can efficiently acquire new skills and solve open-ended problems. That is the ARC AGI definition of AGI. So AI and its current trajectory. So in order to know where this is going to go and how it'll be developed, we must pay attention to what the people who are developing this technology says, where they want to actually steer it, because they are again, driving the boat. So OpenAI, Google DeepMind, Anthropic, and Meta seem to be following a very similar path that they have all vocalized. Okay, OpenAI has specifically laid out their path for all of public awareness. And I have a screenshot of an image on the right here talking about level 1, level 2, level 3, and level 4, and level 5 stages of artificial intelligence advancement. So level 1 is our current paradigm of generative AI that predicts the next token. Largely, this is simply a chatbot, a conversational AI that incorporates natural language processing, giving the ability to speak and program the behavior of the computing system with natural language. Level 2 is the next paradigm of AI that frontier model companies say we are entering, with claims that these models will be able to reason at PhD levels. So far, there's no evidence of these models achieving that level of reasoning, but what we do have is these models achieving silver medals in the International Math Olympiad, which is very impressive, and it is definitely along the way to becoming that PhD level reasoning type of model. Can they do that across all aspects, all categories? We don't know. We just have that International Math Olympiad checkmark example. Level 3, this is the paradigm of AI agents. So this comes after level 2, level 3, where you can simply go to the conversational interface, whether it's ChatGPT or Claude, and you can prompt this large language model or this AI agent to complete any arbitrary task on behalf of you. That is level 3. And then level 4 is the innovators. These are AI agents that can create novel solutions to real-world problems and can innovate in our environment for us. And this has been the mission for OpenAI, to create an AI model that can build itself better than any human can build it. And then finally, we get to level 5, and this is the point in time where AI agents can autonomously form organizations and align themselves with a specific goal to achieve. This will ultimately be possible at level 4 as well, you could reasonably assume. But at this point, they're thought to be far superior than all humans at any tasks. Maybe at certain tasks, we might value the human flaws in certain things, but whenever we get to level 5 AI, there's not really many economically valuable things humans will have left to do, as you could assume. So now all of this sounds very profound, all of this sounds very insane and transformative, but before we come to any conclusions, let's look at all of the arguments, all of the viewpoints, and the actual evidence for arguments on both sides of this technology. Whether you're for it or you don't think it's going to happen, we need to look at both sides and objectively come to a conclusion based off of all of the evidence and consensus that we have. So, what are the theoretical limits of generative AI? There are few limitations that stem from the type of AI that we currently have, and most importantly being the hallucinations, which is basically AI being confidently wrong about a topic when providing answers. So it could be telling you to do any task, or it could be teaching you any information, and it'll say a fact very confidently, but the fact is not true. And this is largely due to the way large language models produce answers from a first principle standpoint. They simply mimic and repeat information that they are trained on. Many relate these current models to a stochastic parrot, and this is shown as System 1 thinking, which is kind of like whenever you hop in your car and you just drive somewhere, you don't really think about it. You use a System 1 frame of thinking where you just kind of mimic past behaviors. While in humans, we have the ability to use something called System 2 thinking, where we can reason through scenarios logically, we can solve problems by relating them to adjacent problems, retrieve knowledge from our understanding of certain topics or adjacent topics, and we can look backwards in time, then extrapolate our reasoning forward into the future, and then with simple thought experiments and extrapolating our thoughts, we can use these tools to help us solve specific problems or more complex problems within the real world, which large language models cannot do. Another issue with LLMs and generative AI is how it produces tokens. If you look at the strawberry test, for example, current large language models, when asked how many R's are in the word strawberry, they answer with the number 2, when there's obviously 3 R's in strawberry, and this is because of the tokenization of the word strawberry when being perceived by these large language models. So I took a screenshot from Claude to ask Claude, how many tokens are in the word strawberry? And Claude said there's 2 tokens in strawberry. There's straw and then there's berry. So the R's are separated by the token, and it goes back to the last token and retrieves the 2 R's from the word berry, which is why whenever it's prompted with how many R's are in strawberry, it says 2 instead of 3, because it goes back to the last token and pulls those 2 tokens instead of going back to the last 2 tokens and identifying that as one word called strawberry. Hopefully that made sense. So what are the theoretical limits of the transformer architecture? We just talked about theoretical limits of the generative AI that we have. Now let's talk about the actual architecture that generative AI is built upon. So there are a variety of current limitations with the transformer architecture that current consumers are aware of. So there's a fixed context length. Traditional transformers operate on fixed context lengths, while some variations like the Transformer XL and Longformer address this by expanding the context window. They still face practical limits on how far they can extend the sequence length. I think OpenAI actually just released a beta test for a 64,000 token output length for certain users to access to test certain capabilities with that type of output length. But largely, the context length is still very limited. Eventually, it'll be a lot longer, maybe even feeling infinite, even though it'll be constrained. So this is something, even with the current transformer architecture, we can necessarily improve. But at the end of the day, it is still very limited, and it's not quite like a human brain or like any type of general intelligence where I don't have a finite amount of context length. I can ramble on for my entire life until entropy destroys my body and I cease to exist as a being at all. Next is tokenization. The way input text is tokenized can affect the model's understanding and generation of language. Suboptimal tokenization can lead to inefficiencies and inaccuracies in model performance, such as the example used with the strawberry test. Next is the model size. As large language models grow in size, example, ChatGPT-3 had 175 billion parameters. The resources required to train and deploy these models increases significantly. Training such large language models demands vast amounts of computational power, leading to high energy consumption and costs. I do think this is going to be something that, as we advance computing technology and as we do more research into the transformer architecture and into using better ways of training large language models or just using better data, there are going to be ways to fix the model size and make the costs of training such models a lot cheaper. But largely, this is a constraint that we must consider. Next is optimization challenges. Training very large models is prone to instability, requiring careful tuning of hyperparameters and advanced techniques like learning rate schedules, gradient clipping, and distributed training strategies. And there's also catastrophic forgetting, such as models that are fine-tuned on specific tasks. They can lose knowledge from the pre-training phase, which is a phenomenon known as catastrophic forgetting. Balancing task-specific fine-tuning with general knowledge retention is a significant challenge that the transformer architecture faces, which is why a lot of people say GPT-4 is getting dumber or Claude is getting dumber. And it's specifically because of catastrophic forgetting, as we just mentioned. And one thing I just want to say, I am positive a lot of these problems, if not all of these problems, are being addressed internally right now and we're probably getting a lot of progress on these things. But nonetheless, these are current limitations that are known and are important to address when coming to a conclusion on this topic. So if you ask me, I'm willing to bet there are solutions that are being pretty much, like, a lot of these problems probably have reasonable solutions to already internally, but we just don't know it yet. I don't know for sure. That is just my bet, just because I know there's a lot of capital and a lot of talent focused on this one specific industry, and research papers are going out at extremely high velocities right now. So, what are the theoretical limits of classical computers? So, now we're coming down to the very first principles of the hardware that these large language models are built upon. We talked about the software, generative AI itself. Then we talked about the transformer architecture. Now we're talking about classical computing in general. We're breaking it all the way down to the very first principle so we can diagnose the problem and reverse engineer it, okay? So classical computers face several theoretical and practical limits whenever it comes to this technology. These include computational complexity, resource constraints, data limitations, energy consumption, algorithmic bias, ethical considerations, and fundamental theoretical boundaries. The largest constraint with classical computing, however, is the processing power it takes to create such a powerful AI system. It literally takes a comparable amount of electricity that it would take to power an entire city just to train one of these large language models. And there are other theoretical reasons as to why classical computers aren't sufficient to solve such a problem as AGI. And one of them is Gödel's incompleteness theorem, which states in a consistent formal system that is capable of expressing elementary arithmetic, there are statements that are true but cannot be proven within the system. An implication of this is for AI and large language models, this means there will always be true statements or properties about numbers and about computation that these systems cannot prove or fully understand. Classical computers operate based on formal systems, which are deterministic systems and algorithms, which means they are subject to the same limitations Gödel identified. This constrains the extent to which AI can achieve certain types of reasoning or provide certain truths. Large language models like GPT-4 use statistical methods and pattern recognition rather than formal proof systems. However, the underlying computational infrastructure still operates within the bounds of these formal systems. This means large language models might generate or encounter statements they cannot prove or fully justify within the training and logic. These systems can approximate understanding but cannot achieve complete comprehension of all possible language constructs or logical statements. In essence, new hardware and new paradigms of computing could be required for AI systems that reach human level capabilities. But again, this is something that is theoretical. It is entirely possible that as we scale this infrastructure on a classical computer, we see emergent properties and behaviors that would be comparable to a human brain. But from what we know of neuroscience, I think it's very unlikely. So speaking about neuroscience, we're talking about neuromorphic computing and the neuroscience of the brain. And at some level, neural networks in artificial intelligence and in neuromorphic computers simulate the functionality of the human brain. Neuromorphic computers, on the other hand, are mainly focused on emulating the behavior of the brain using spiking neural networks, while the machine learning transformer architecture is more so just that, machine learning, and it's not really simulating the behavior of the brain. It's more so simulating retrieval of information and being a stochastic parrot like we mentioned previously. The thing about neuromorphic computing, however, and the reason why we aren't focused on building these systems on this type of computing is because it is much harder to scale and uses much more energy than the original architecture that large language models are built upon. A notable research paper from Dr. Kristen Kerskens, a lead physicist at the Trinity College Institute of Neuroscience, he discussed the quantum effects that we do see in the human brain, and we do know that there isn't just some classical deterministic computer that computes within our brain. It is some type of probabilistic or even a phenomena of superpositions that happens within our psyche. It is likely that quantum processes are an important part of our cognitive and conscious brain functions. So the way I look at this is I look at it like a continuum. On one side, we have classical deterministic computers off of transistors that are using the transformer architecture to make large language models that we have today. That is our current architecture. Somewhere in the middle, I'm assuming there's some type of thermodynamic computing device with a new architecture that we can build AI on top of. And then all the way on the most sophisticated, interesting, complex type of architecture, we have quantum computing, computing that has a different type of architecture that we can build AI on top of. And on here is a spectrum of least conscious to most conscious. And as we scale towards quantum systems, we will be able to surpass the human consciousness, surpass everything we thought was possible intellectually, and things just get very interesting, to say the least. I don't know that for sure. This is my assumption. I'm assuming that as we develop quantum computers, like we did with transistors, we will see emergent properties and capabilities of those computers. So again, take that for a grain of salt. That's just my theory. But let's continue through the slide. Dr. Kerskens also mentioned that quantum brain processes could explain why we can still outperform supercomputers whenever it comes to unforeseen circumstances, decision making, or learning something new. Our experiments, performed only 50 meters away from the lecture theater where Schrödinger presented his famous thoughts about life, may shed light on the mysteries of biology and on consciousness, which scientifically is much harder to grasp. Next is energy and cost. So we already know the biggest bottleneck to artificial intelligence is the energy required to make it globally adoptable and commercially scalable in the humanoid form, or just in a large language model or an agentic form where it can actually take actions in the real world, whether it's in a virtual environment or the physical environment. The cost associated with that energy is astronomical, and Sam Altman is on the board and is an investor of many different nuclear energy companies, whether it's fusion energy or fission energy. He has about a few companies in each category that he is associated with, and he is betting that that technology will be able to supplement the AI infrastructure needed for this to become commercially scalable across the globe. And Donald Trump is also somebody who wants to make nuclear energy a main provider of U.S. energy if he gets elected for president. So these are possibilities that are very likely in the future if these things do happen. It is very likely that we will have nuclear energy that can sustain the infrastructure for these large language or not even just large language models, but for AI agents, humanoid robots, robo-taxis, or any type of AI system within the actual environment of the physical world. We are making massive progress with nuclear fusion, and OpenAI is betting that it will be commercially ready for OpenAI specific intended use by 2029. And Sam Altman has a partnership with another fission company as well, just to make sure that they have nuclear energy, just in case we don't achieve fusion by 2029. Nonetheless, even if that doesn't happen, the goal for thermodynamic computing, which is Guillaume Verdon's startup, and quantum computing, is that these things will be somewhat commercially viable at a very small scale by 2030, which would give us the platform needed to build artificial general intelligence in not too long from now. And if nuclear energy is provided as well, along with these different paradigms of computing, well, the world is going to look very different, and it's going to be one hell of a ride for all of us, to say the least. But all of this to say, are we really in a bubble? In my opinion, the short answer is no. Even though the current architecture we are building AI on won't get us to AGI, we don't need AGI to revolutionize the way all humans approach work, thinking, brainstorming, completing tasks, writing, producing media or content, advertising, etc. All of the things that I just listed are already being augmented by AI without anything even relatively capable. Like, these systems that we have today are kind of shit compared to what they're going to be in just a year or two from now. Yet they're very powerful and are augmenting almost every single person in the workforce that is deciding to adopt it, at least. And there are an unlimited number of ways to augment your labor and augment your intelligence with this technology that a lot of people haven't even figured out yet. So the big question, however, is, are we going to see AGI or artificial superintelligence soon? And I'm not entirely sure. We very well could see an early stage of AGI built on classical computers, but just not deployed nationally due to power constraints, unless we achieve some type of nuclear energy that would allow it to be deployed globally or nationally. Or maybe it's impossible altogether to have that type of emergent capabilities on a classical deterministic computer. Either way, I don't think anybody truly knows, and we don't have evidence to prove if either side is correct, whether you don't think it's going to work or you do think it's going to work, there's no way to prove either way. We have theorems for the one, and we don't have theorems. Well, actually, we have theories for both sides, and we don't have evidence for either side, and consensus is split 50-50 down the middle. So both sides are arguably wrong. But overall, I think people saying we are in a bubble are either incentivized to think we are because it will affect them negatively short term, or they're just looking at the entire picture in a short-term lens altogether. My prediction is that we are not in a bubble, and we can still have reliable AI agents that fundamentally change labor as we know it without achieving artificial general intelligence. But eventually, I think we could achieve AGI within the next decade as long as we don't screw up at a geopolitical level. Now, more importantly, I think the real question is, how can we make sure that whenever we do get to the point of having AI systems that are as capable or more capable than humans, how can we make sure that they are something that doesn't become completely alien to us? How can we make sure that we always understand the complexities of the solutions that they're coming to in the real world? Like, whenever these things get to the point where they're creating novel solutions that we don't understand, we need to make sure that we can actually grasp these concepts, at least for a while. Maybe one day they'll solve such complex problems that it's fundamentally impossible for us to even theorize, but we need to make sure that we can communicate with these things as the best possible way that we can, to say the least. I personally am very much a believer of Stephen Wolfram's observer theory that says our physics, our math, and our perception of reality has everything to do with the fact that we are the types of observers that we are in the universe. And if we were a different type of observer in the universe, we would then have different ways of explaining our perception of reality in terms of math and physics. So an interesting thought experiment would be to ask, what if we could create an AI system that can fundamentally understand everything, and it even becomes smarter than us, and we can communicate with it? And then we have that AI create a different AI that is a different type of observer than us in the universe. And that different AI can understand different phenomena of the universe that we can't even experience for ourselves just because it's a different type of observer in the universe that we're in. What if it can go to other dimensions or experience other dimensions and say, whenever you move this mouse pad, it actually does something in a different dimension that you can't even see, you can't even feel, you can't even sense it at all, because we are the types of observers that we are in the universe. A good way to think about this would be a bat flying around in the dark. A bat is very good at hearing things, but it's basically blind. The universe to a bat is completely different than the universe to us. But for the bat, this sound that it has and the feeling that it has of the physical world is still within the third dimension that we are in. Therefore, it is still something that we can experience, and it can experience us, and we can have similar capabilities or similar senses as far as auditory or touch or taste. These are things that we share. But what if we create some type of system that has senses that we can't even comprehend, and it can experience a different plane of reality altogether? And then we can communicate with a different AI that communicates with that AI that experiences that different plane, and it can explain what that plane actually is like to us. I think these are much more interesting questions that we should actually be focusing on. Instead of saying, let's make sure AI doesn't work, or I don't think AI is going to work, let's ask, how can we make sure it works so that we can understand more about the world that we live in? All of the other things of like doom or foom or all that bullshit is simply that. So approach this with a positive lens, understand that it's simply a tool, and as long as we use it for positive things are most likely to happen. And I think it'll be a very, very beautiful world where we understand the realm of physics much better than we did before. And we'll be able to achieve different technologies and different capabilities that ascend us through the cosmos and make us become a type 2 or type 3 civilization in the future and give us a much greater experience of reality overall.